Okay, let's just think about this for a second. That last message you sent.
Yeah.
Maybe it was a photo, maybe just a quick text. The person could be in the next room or, halfway across the world.
Right.
You tap send and boom, it arrives almost instantly. We just expect that now.
We do. It's the standard.
But getting that to work, achieving that low latency and just absolute reliability for millions of people all at once. That is one of the biggest challenges in modern engineering.
It's a massive, massive feat. And you can't just hope it works. You have to build that reliability in from the very foundation. So our mission in this deep dive is to get right into the nuts and bolts.
Past the surface level.
Exactly. We're going to break down the core architectural pieces, the queues, the proxies, the databases, and look at the actual design choices that let a system like this handle that insane traffic, all based on materials detailing these, high-performance real-time architectures.
So it's not just about the components. It's the strategy behind them. And that really starts with the core problem, right?
Yeah.
How do you even begin to manage a constant flood of messages sending, receiving, storing, without the whole thing just seizing up?
Well, the main challenge is traffic. You have millions of users sending messages at the same time. If every single one of those messages had to wait for a full synchronous round-trip confirmation from the back end,
The system would just bottleneck instantly.
it'd be like rush hour traffic where every car has to stop for a full inspection before the next one can move. It just doesn't scale.
And this is where the system uses one of its most clever tricks to keep up that feeling of instant. It's all about asynchronous processing. The sources had a great analogy for this.
They did. It's the difference between a phone call and a text message.
Okay.
A phone call is synchronous. Both of you have to be there, connected at the same time for it to work. You're both tied up. But sending a text, that's asynchronous. The second you hit send, your phone gets a little signal back, an ACK, that basically says the message has successfully left your device. It's been published.
And that immediate ACK is the magic trick. It frees up your phone, your connection, immediately.
Exactly. The system says, I got it, don't worry, I'll handle it from here. And then all the hard work, the routing, processing, finding the recipient, that all happens in the background. Technically, this all relies on something called non-blocking I/O, which just means the server doesn't wait for one job to finish before it starts the next million.
So that idea of decoupling, separating the sending of the message from the processing of it, that leads us right to the first big component, the message queue.
The message queue is really the backbone of this whole asynchronous system. It's, like you said, a kind of digital postal service.
Well, why can't we just, dump everything straight into a database? Why do we need this extra layer?
Because systems fail, and messages have to be durable. They can't just vanish. Platforms like RabbitMQ or, at this kind of massive scale, Kafka, are built for one thing: handling streams of messages reliably.
So they decouple the sender from the receiver.
Yes. So if the receiver, say, the little service that's responsible for pushing a notification to an iPhone, if that service gets overwhelmed or crashes,
The messages don't get lost.
they just sit safely in the queue, waiting. It buys the whole system time to recover. It's a huge boost for resilience.
Okay, I get it. But help me picture this. If the queue is the safety net, couldn't the queue itself become the new bottleneck? What stops it from just filling up?
That is a critical question, and it comes down to how these queues are designed. For a huge system, you'd probably use something like Kafka, which is basically a distributed log. It achieves parallelism through something called partitioning.
So it's not one single line, it's hundreds of them.
Or thousands. Messages get spread out across all these partitions. And if you're smart about your partition key, maybe you tie it to a user ID, you can guarantee that all messages from one person are processed in the right order, while the system as a whole can just absorb this enormous load. It's resilience through distribution.
I like that. Resilience through distribution. Okay, but at some point, these messages have to be stored permanently. So that takes us to the digital archive, the database.
Right. And for a system with billions of messages, your choice of database is, well, it's everything. It has to handle this really weird mix of problems.
What do you mean?
It needs to handle incredibly high write loads. Every single message is a new write, but also massive read loads, like when you scroll back through a year of chat history. And it has to keep everything consistent.
I can just imagine the engineering meetings, the classic dilemma, relational versus NoSQL, speed versus consistency.
Oh, absolutely. The sources really dig into this tension. A relational database, like Postgres, is amazing at guaranteeing consistency,
Hmm.
but it can really struggle with the sheer volume and velocity of writes at this scale.
And that's where NoSQL comes in.
Precisely. A NoSQL database like Cassandra is built for horizontal scalability. You can just keep adding more machines to handle more load. It's amazing for simple lookups like, get me all messages for this user ID.
But the trade-off is
Yeah.
consistency.
Often, yeah. The consistency guarantees can be a bit looser, and doing complex queries is harder. But for retrieving chat history, the speed and scale of NoSQL usually wins. It's a strategic trade-off.
So you accept a little complexity on the retrieval side to gain this massive throughput on the right side.
That's the game. And once that data is stored, the next challenge is not hammering the database every single time someone opens the app.
Right. Which brings us to speed multipliers. We need a caching layer.
The caching layer, yeah. Using something like Redis or Memcache, this is non-negotiable for reducing latency. It's all about storing the data that's volatile but accessed all the time.
So things like who's online or offline, your friend's profile picture.
Exactly. User presence, metadata, and maybe the most recent messages in a chat. That stuff lives in the cache.
So when you open a chat, that first screen of messages is already waiting for you in high-speed memory. You don't even have to ask the main database.
And that's what makes the experience feel so snappy. Retrieval time drops from milliseconds to microseconds.
Okay, that covers text. What about media? A photo or a video file is way bigger than a text string. And if I'm in London and the server is in San Francisco, that's a long trip for that data.
It is, and that's why you have to use a content delivery network, a CDN. It's absolutely critical for a global service. When a user sends a video, that file gets stored, and then copies of it are immediately pushed out to edge locations all around the world.
You're basically moving the media closer to where the users actually are.
Correct. So when your friend in Tokyo opens that video, they're not pulling it from a server in California. They're getting it from a CDN node in, say, Singapore. It physically shortens the distance the data has to travel, which makes a huge difference in loading times.
Okay, so we've got the data flowing, it's stored resiliently, and it's optimized globally. But now we have millions of people trying to connect to the front door all at once. We need some kind of intelligent traffic cop.
We do. And this is where a tool like Envoy Proxy comes into the picture.
Yeah.
It sits at the front door and acts as a reverse proxy and a very, very smart load balancer. It mediates all communication.
A simple load balancer just spreads traffic evenly.
Yeah.
But you're saying Envoy is more sophisticated than that.
Much more. Because it operates at the application layer, it can actually understand the traffic. It can make routing decisions based on real-time factors, like the health of a downstream server, or even the priority of a message.
So if one of the chat servers starts to get overloaded or slow down,
Envoy sees that happening in real time and just stops sending new traffic to it. It protects the system from itself, and because it's programmable, it can also handle things like authentication and rate limiting before the request even hits your main application logic.
but for Envoy to make those smart decisions, it needs to know what's happening everywhere, all the time. It needs data, which brings us to monitoring.
Precisely. You can't manage what you can't measure. And for a complex distributed system, the tool that comes up again and again is Prometheus.
Okay.
Prometheus is designed to pull in time series metrics from every single component in the architecture. The proxies, the queues, the databases, every single application server.
And what are the vital signs? What are the key metrics that engineers are watching like a hawk?
Latency is number one. Specifically, P99 latency, the experience of 99% of your users. You also track queue depth, server CPU and memory, and, critically, error rates. Prometheus pulls all this together so you can spot bottlenecks before they become full-blown outages.
So this monitoring isn't just for looking at pretty graphs. It's an active defense system.
It is, and it feeds directly into one of the most powerful resilience patterns out there, the circuit breaker.
The circuit breaker. I love the name. It's designed to stop what? A cascading failure.
Exactly, the digital domino effect.
Explain how that happens.
Okay, imagine one chat server starts to struggle. Maybe its connection to the database is slow. If all the other services keep hammering it with requests, they'll start to time out waiting for a response. Their own resources get tied up. Pretty soon, they start to fail, and they take down the services that depend on them.
And the whole system unravels.
The whole thing can come crashing down. So the circuit breaker wraps around that initial failing service. It starts in a closed state, letting traffic through, but it's counting failures.
Okay.
If it sees too many errors in a short period, it trips and moves to an open state.
And when it's open?
It immediately rejects any new requests to that broken service. It just fails fast. This stops the upstream services from getting stuck and protects the rest of the system.
But how does it know when things are fixed? Does someone have to flip it back on?
No, that's the beautiful part. It's automated. After a certain timeout, it moves to a half-open state. It lets just one single test or request through.
Little probe.
Exactly. If that request succeeds, the circuit closes again and traffic resumes. If it fails, it flips back to open and waits again. It's a self-healing mechanism that prioritizes system stability above all else.
That's just fantastic design. You're engineering for failure, not just for success.
Okay, so we've covered components, we've covered resilience. But to get back to that initial challenge of massive scale, you need more than just good components. You need an overarching strategy.
You do. Because just adding more servers will only get you so far. Eventually, your database will still be the bottleneck, so you have to be more strategic.
Yeah.
The sources point to 3 main pillars for achieving this kind of hyperscale.
Let's start with the big one, database sharding.
Sharding is basically splitting your giant database into many smaller, independent databases, or shards. So instead of one database for the whole world, you might have hundreds. This spreads the load.
But that sounds incredibly complex. How do you decide which data goes on which shard? If you get that wrong, you could still have one hot shard that's doing all the work. That is the million-dollar question. For a chat app, you'd typically shard by something like user ID. But what if one user is a celebrity with millions of followers? Their shard could get overwhelmed. So you need really sophisticated routing logic, and sometimes you even have to re-shard move data between shards, which is a terrifyingly complex operation to do live.
Okay, pillar 2, connection management. This is unique to real-time systems, right? We're not talking about simple web page requests.
Not at all. Chat apps need to maintain millions of open, persistent connections using protocols like WebSockets. The challenge is making each of those connections super lightweight and stable. If every idle connection uses up too much server memory, the system will fall over from the sheer number of users just being online.
And the final pillar is message routing. So if my connection is on server A, but my friend's history is on shard B, how does the system know where to send my message?
You need a super fast internal mapping service. It's like a directory that knows in real time which chat server every online user is connected to and which database shard holds their conversation history. That map has to be insanely fast and always available, otherwise messages just go into a black hole.
The whole thing sounds less like a static architecture and more like a living organism,
Yeah.
a self-regulating system that's constantly monitoring and adjusting itself.
It is, which is why the final piece is just relentless vigilance. All of this complexity only works if you have hypersensitive alerts on those key metrics. If P99 latency spikes for more than a minute, alarms have to go off. Without that automated real-time feedback loop, even the best architecture will just silently degrade.
Wow. So this deep dive really shows that the simple act of sending a text is powered by this incredible global orchestration of queues, sharded databases, smart proxies like Envoy, and these critical fail-safes like the circuit breaker. It's really a masterclass in designing for scale, speed, and reliability.
Yeah, and what really stands out to me is that the system isn't just designed to work. It's explicitly engineered to survive when parts of it break. It's constantly taking its own pulse with tools like Prometheus and automatically protecting itself with those circuit breakers.
And that actually leads to a really interesting final thought for you, the learner, to take away from all this. If a system at this scale is constantly monitoring its own health, actively tripping circuits, and rerouting traffic all by itself just to stay stable, what does that tell us about the level of automation that's required in any critical system design? And maybe more importantly, when the machines get so good at this kind of automated resilience and self-healing, where do we, the humans, the strategic decision makers, fit into that loop? It's something to think about the next time you watch that little status indicator instantly flip from sent to delivered.